Hello everyone, I'm Wuyang Li, and I'm happy to present our research titled Adjustment and Alignment for Open-Side Domain Adaptation. In this field, we observe that the model trained in the label source domain cannot discover satisfactory novel class regions hidden in the image, and it tends to wrongly recognize novel regions as some non-correlated base classes. To explore this issue, we build a structured causal model and formulate this issue as the bias learning between the base and the novel class. Inspired by the causal debiasing, we propose a theoretical solution and give a task-driven mathematical derivation to get a simplified and deployable solution. Then, we connect the theory to the practice with an adjustment and alignment framework, which consists of a frontal adjustment module to achieve unbiased learning in the source domain, and a decoupled causal alignment module for an unbiased cross-domain transfer. Finally, the debiased model has a good scene understanding with the perception of base and novel classes. Now, we will move to the details of this work. This is the outline of this presentation. Open-side domain adaptation is a real-world friendly setting to simulate the learning of the novel class and the novel domain. In the training stage, we consider a labeled source domain and an unlabeled target domain, where the target domain has private novel class samples. In the inference stage, we aim to classify the base classes and identify the novel classes as unknown in the target domain. Previous studies in this field have focused on three aspects. In the source domain, they train a closed-set classifier with labeled base class samples. In the target domain, they attempt to separate the base and novel classes in an unsupervised manner. After that, they align the base class distribution between the two domains. The motivation driving this research stems from an observation. As shown in the figure, we observed that even though the image is labeled with chair, there are variant semantics hidden in the image, such as the yacht, sea, and the ground, which are out of the labeled class space and should be considered as the potential novel class. However, we visualized the activated regions in existing works and find that they cannot discover these novel class regions well. Moreover, we give a prediction on each pixel before the average pooling layer and observe that there are novel class regions wrongly classified as some non-correlated base classes. Hence, existing works fail to recognize these novel class regions caused by the bias between the base and the novel class learning. To explore and justify this bias, we propose a structured causal model to formulate the open-side domain adaptation task, which mainly contains two causal links. The first link indicates pulling the pixel-level feature into image-level representation, and then separating it into several classes, which can be seen as a standard image classification. The second link represents that the unobservable open-side context determines the image composition and the label distribution. Hence, we can observe that the open-side context is the confounder leading to the bias learning. In the causal theory, the backdoor and front-door adjustment are two solutions to address the bias, which aim to decouple the variable c and x respectively. The unique advantage of front-door adjustment is the ability to handle the unobservable confounder, which motivates us to design a corresponding causal solution. So, we implement the front-door adjustment in open-side domain adaptation. Concretely, we first open the summation operation by considering the decoupled base and the novel class regions in the pixel-level features. And then we simplify the equation by removing justified terms to get the final objective of this work. If we look closer at the objective, we can find that existing works only consider the base class terms in the source domain and align the base class distribution. So, we aim to optimize and align the base and the novel aspects. Based on the analysis, we further connect the theory to the practice. Considering a biased classification baseline, we propose front-door adjustment to correct the bias learning in the source domain. And then, we design a decoupled causal alignment to transfer the debiased model to the target domain unbiasedly. In the first module, we first observe and define three types of regions in a labeled image, including the main body consistent with the image level label, the regions in the base class that hasn't been labeled, and the potential novel regions out of the base class space. Hence, according to the adjustment equation, we first explore the novel regions with a score ranking mechanism. Then, we estimate the conditional probability within the training batch and implement the optimization objective with the base and the novel class terms in the source domain. In the second module, we aim to align the base and the novel class distribution at the region level. To achieve this, we first generate the orthogonal mask to decouple images into base and the novel class regions, which considers the base and the novel class prediction confidence. Then, we conduct an adversarial-based domain alignment to transfer the base and the novel class distribution in parallel. To justify the debiasing effect, we first remove the average pooling and directly make predictions on pixel-level features. We find that the unbiased model can make correct predictions on these novel regions. Moreover, for the image-level prediction, we also find that the model has a satisfactory novel class perception. For the benchmark comparison, the proposed unbiased model achieves good performance gain on the novel class accuracy and gives a satisfactory trade-off between the base and the novel class performance. This verifies the advantage of the debiasing effect. In this work, we observe the bias in open-side domain adaptation and formulate with causal theory and propose a theoretical solution. Then, we connect the theory to practice with an adjustment and alignment framework and achieve good performance on benchmarks. Thanks for your listening.